Hello again. Let's do the second half of chapter 14. So we've been talking about time series models, autoregressive models, and autoregressive distributed lag models. And let's now talk about statistical inference, how we can use these models to test things. And so the first topic we're going to, so we can estimate an ADL of P Q1 to QK by OLS if the assumptions we talked about at the end of the last video hold. They're consistent, they give you the best forecasts and so on, the test statistics are correct. In chapter 15, we'll talk a little bit about what happens when some of these assumptions don't hold, like the assumptions about the errors being uncorrelated with the right-hand side variables. So the first thing we'll talk about is Granger causality. So what we want to know here is whether one variable helps to predict another, whether one variable helps to cause another variable. So we might want to know, does the federal funds rate help to predict GDP? Does monetary policy work? And so we could use a Granger causality test to look at what we'd call money-income causality. Do changes in monetary policy affect output or not? And these are very simple tests to conduct because they're nothing more than a standard F test. So there's some theory behind them you would learn if you go on in econometrics, but we don't really need to have that. So let me just look at let's use, what is this? An ADL of P, Q1, and Q2. So let's just have two x's. So that means yt is beta naught plus beta 1 yt minus 1 plus beta p yt minus p plus delta 1 1 x 1 t minus 1 out to delta 1 q1 x1 t minus q1 plus delta 2 1 x2 t minus 1 delta 2 q2 x2 t minus q2 plus an error term. So that's the standard ADL for two x's. And we want to know does x2 cause yt? So maybe this is the federal funds rate, and this is the interest rate. We might have the price level in this model as a third variable and so on. And we want to know, does the federal funds rate x2 cause output yt? It's just a simple F test. So the test is simply the null is that all of the deltas, delta 2 1 equals delta 2 2 equals delta 2 q2 equals 0. Are all the deltas jointly 0? The alternative is at least one is non-zero. And it's just a standard F test. In Stata, you would just say test the delta 1, delta 2 1, delta 2 2, and so on. delta 2 Q2 equals, or you don't need zero, just somewhat, I think I wrote this right, but you get the idea. It's just a standard test statistic. So those are Granger causality tests. They're used extensively in macroeconomics whenever we want to try to answer that kind of a question. There's some other things you use too called impulse response functions. We'll look at in the next chapter. But that's mainly what you want. Okay, again, for the general ADL model, let's go back to forecasting. Uncertainty, that's the root mean square error stuff. And forecast intervals. So uncertainty and confidence intervals. So one measure, the one we're going to use, of uncertainty is, well, we already talked about the root mean square forecasting error. If we assume UT is normal, and we'd want to think about that assumption before assuming it, we can also construct confidence intervals. And there's really nothing new here for either one of these, but let me just note everything quickly. So as we've said before, there's two sources of forecasting uncertainty. Forgot to note what time I started. It's two sources of forecasting uncertainty. First, we don't know future UT. We don't even know the min sample. But at least we can get an estimate of them. We don't even have that here. And two, there's the uncertainty due to using estimated coefficients instead of the true value. And we said when n is large, when t is large enough, can ignore 2, the estimated coefficient, because as t gets bigger and bigger, we get closer and closer to the true values. So this gets really small when t is large. Can ignore 2 and use the standard error of the regression as an approximation of the root mean square forecasting error. But in general, when working with time series, macro time series data, both are important. So we're not going to be able to use this simple way out of just reading the SCR off our printout and saying, that's fine, that's good enough estimate. So what do we do in that case? Well, most packages will do this automatically So I'm not going to spend a lot of time on it because you won't ever have to actually do this, but you do need to understand it. So assuming homoscedastic errors, so we need that assumption for what we're going to do. The forecast, so let's use an ADL 1-1 to illustrate. So the model that we have is yt equals beta naught plus beta 1 yt minus 1 plus delta 1 xt minus 1 plus ut. Then the forecast, the 1 period ahead forecast, would be yt plus 1 given t hat is beta naught hat plus beta 1 yt plus delta 1 xt. These are hats. So that would be our forecast. So then the forecast error would be what? It would be yt plus 1 minus y hat t plus 1 given t. If you just write in what yt plus 1 is and what y hat is, you can show that this is equal to, fairly simply, ut plus 1 minus beta naught hat minus beta naught plus beta 1 hat minus beta 1 yt plus delta 1 hat minus delta 1 xt. So that's just this. Just plug in these two definitions. Write this as yt first, and this will pop right out. Or write this as yt plus 1. You get the ut plus 1. Then there, you can see the subtractions. That minus that, and so on. So this is a zero mean homoscedastic process. And so this has zero mean, and the variance is sigma squared u. And it's independent of the other term. This is independent of this. That's what our assumptions do for us. We know that ut is independent of all past data. That was one of our assumptions. And then these hats are all dependent upon the data. And so if ut plus 1 is independent of past data, then those are independent. So when we take the variance of this, we want the variance of this. We want the expected value of this squared. We can just take this variance plus this variance. So using that, the mean square forecasting error, not the root, without taking the square root, the mean square forecasting error is the expected value of yt plus 1 minus y hat t plus 1 given t squared. And that's going to be equal to sigma squared u. This is just the variance. That plus the variance of all the terms in the brackets, beta naught minus beta naught hat plus beta 1 minus beta 1 hat, yt plus delta 1 minus delta 1 hat xt. And I won't bother to calculate this. One could. So when we use stata, it will use this formula for us. And if n is large, no problem. This will just be a small term. We'll still get an accurate estimate. All righty. Now let's look at forecasting intervals. This is something I wish the news people would report even the government reports it, but you don't have to hear it. When you hear the GDP forecast for next quarter is 1.9%, first thing you should think of is plus or minus what? When you hear that employment this month grew by 180,000 workers, what if that's plus or minus 130,000? Which is not a bad, when you look at how accurate those forecast estimates are, what it tells you is you really, when the government puts out a monthly forecast like that, you really shouldn't, or anyone, you really shouldn't put a lot of weight on it because it probably has a huge, huge standard error around it. So this is the title of this section is Forecast Intervals in the book. If we assume ut plus 1 is normally distributed and homoscedastic, the 95% forecasting interval is y hat, the estimate, t plus 1 given t, plus or minus 1.96 times the standard error of yt plus 1 minus y hat, t plus 1 given t. And you can get that off the printout, as always. And so there's really nothing new here in terms of estimating the confidence intervals. If you don't have homoscedasticity, the book talks about that in section 16.5. You can read ahead. We're not going past chapter 15, but there's ways if you've got heteroscedasticity to deal with this. Those are something called arch models, autoregressive conditional heteroscedasticity. And they're mostly used in finance, but we're not going to get there. Okay. Determining lag length. Before we do anything, we need to know what is P, what is Q1, what is Q2, QK. How many lags should we include? The basic rule of thumb is that if you don't include enough lags, you make a big error. You bias your coefficients, and your estimates and your forecasts are going to be way off. If you include too many lags, it doesn't bias anything, but reduces the power of your test. It also reduces the accuracy in some sense, but it makes your estimates less powerful. But if you're going to make a mistake, including too many lags is a much better mistake to make than including too few. Too many, essentially it makes it harder to reject the null hypothesis. Too few gives you all sorts of bias and other sorts of problems. And so generally we want to try to, if we're going to make a mistake, make that one that gives us too many lags. Okay. So there's two basic approaches to doing this. So there's an F-test approach. And there's an information criterion approach. This is the one the profession tends to favor. You see this a lot, and let me go through it quickly and explain what might be wrong with it. So what you do for the F-test approach is you start with a large value of P. So let's just talk about the AR model for the moment. So this is just an ARP, Y on its own, on P of its own lags. So I think probably 4 is enough. Maybe I start with an AR6. So, and then test. So, for example, estimate an AR6. Then test whether that beta 6 equals 0 versus it's not 0. Now, presumably, if you've done this right, this first test is going to be 0 if you've taken way more lags than you need. So you find that you can't reject that beta 6 equals 0. So now, cycle back and estimate an AR5. I should be writing another one here, but I'm going to run out of room, and I want to just show you that how you do this. So now you estimate an AR5. You test that that last lag is 0. If you can't reject that it's 0, go back to an AR4 and test whether that coefficient, whether that variable, the fourth lag, belongs in the model. When you reject that the beta equals 0, you stop. So let's just take 3 lags. So suppose I think 3 is going to be more than enough. Yt equals beta naught plus beta 1 yt minus 1 plus beta 2 yt minus 2 plus beta 3 yt minus 3 plus ut. You estimate and you test that beta 3 equals 0. If fail to reject, estimate yt. If you did reject this one, you probably didn't include enough lags. You may want to start over with more lags. Make sure that very first one is a 0. Estimate yt equals beta 0 plus beta 1 yt minus 1 plus beta 2 yt minus 2 plus ut. Test that beta 2 equals 0. If it's not, you'd estimate an AR1. You may end up with no lags, and so on. And you continue until you reject that the coefficient is 0. So if I rejected that beta 2 equals 0, then I'd want to estimate an AR2. If I didn't reject this with 0, but rejected beta 1 equals 0, then I'd estimate an AR1. So that's the F-test approach. The drawback on this it's very easy to do. You just keep doing a bunch of regressions and F-tests. The drawback is it tends to produce too many lags. Even though that's less of an error than too few, this one tends to go a little overboard on that score. And so the reason is that just out of randomness, you're likely to find that a coefficient's non-zero. So if I start with 20 lags and I only need 2, and I start going back, the statistics are that probably one of those lags are going to be non-zero. And I'm going to end up with, maybe the 10th one is non-zero just because of randomness. Well, then I'm going to end up estimating AR10 when an AR2 would do, and it's just not going to be a very good model for that. So there's 2 alternatives to this called the BIC and the AIC that we'll look at next. And these are the ones that most people in macro use, particularly this one called the AIC. So an alternative are these information criterion approaches. So the first one is called the, there's two of them, it's called the Bayes information criterion. And you usually see it as BIC. It's also called the Schwartz, SCH, yeah, SCHWARZ information criteria, in which case it's the SIC. So you see it designated both as the BIC and the SIC. It's exactly the same thing. So for P lags, I'll just call it the BIC. The BIC is equal to the log of the sum of squared residuals for the ARP model over T plus P plus 1 times the log of T over T. So this is the sum of squared residuals from your ARP. The T is just the number of observations. This is the number of lags. And I hope you know what a log is by now. This is a lot like an adjusted R squared. So remember that when you add another variable to the model, the sum of squared residuals cannot go up. Because it can always make the coefficient 0 and produce the model without it. And so that sum of squared residuals, which is what it minimizes, when you do OLS, that's minimized, can always be reproduced. So you can't possibly have the sum of squared residuals go up. You can always just zero out that other variable by making that beta p equal to 0. And so, and generally, it'll go down. So what we did with R bar squared was we added a penalty that made R squared also go up when another variable is added. So we have one term pushing it down, one term pushing it up. And when that term pushes it up, we know we've gone too far in terms of adding our lags. You could use R bar squared to choose your lags. Don't do that. Not a good procedure. This does the same thing. When we add another variable, the sum of squared residuals will always go down, but this will go up because p plus 1 will get larger. And so we'll keep adding variables until this term dominates. So what you would do with the BIC is you'd estimate an AR0 first, then an AR1, and calculate the BIC. AR1, calculate the BIC. All the way down to the ARP, where P is chosen generously. Calculate the BIC. Then you'll choose the P where BIC is minimum. So you do an AR0, use this formula. This would be a 1. T's will be the same. This will be the sum of squared residuals. That would just be yt equals beta 0. You'd estimate that model. Just gives you the mean of yt. Then you'd estimate yt, or plus ut, is beta naught plus beta 1, yt minus 1 plus ut. You get a different sum of squared residuals, a different p. Now p's 1. This will be 2. Different number here. Generally, what this will look like as you move from, so this is the BIC, and this is P, so here's 0. You'll get something that looks like this. And then you want to choose that P as your lag length. So you just calculate these. Like if I said, I want to know, should it be, I could do this for 0 through 6. I'd run 6 different regressions, run 6 different BICs, and then just choose the lag length associated with the smallest BIC. So it's a fairly simple procedure to do. This has the property that, let me write it down. This has the property that it's a consistent estimator of P. Now that means you're just as likely to have too few lags as you are to have too many. But our errors are asymmetric. Too few is a bigger problem than too many. And so when you have that sort of asymmetric loss function where on one side the costs are much larger than the other side, you usually want to shade towards the good side. So you're less likely to end up in that place where things really fall apart. So there's an alternative called the AIC that does that. So the AIC, the Akaike information criterion, the AIC, this is the one that's mostly used in practice. So the AIC of P is equal to the log of the sum of squared residuals at P over T, so far exactly the same. What it does is add a different penalty. The other one was log of T, which is going to be bigger than 2 almost always, unless T is like really small. And it won't be. Even then, it might not be true. Yeah, this is smaller always. So, so this has a smaller penalty for P going up than the BIC. So what that means is a smaller decrease in the sum of squared residuals is needed to justify having the regression in the model. Needed to justify including another lag. And that implies there's a tendency to estimate longer lags than the BIC. The AIC is slightly biased towards finding lags greater than the true number. But we actually want that bias because half the time we don't want to have a model that we have far too few lags. In practice, I think in the problem I gave you, these come out the same. I can't remember. But in practice, they're often not very different. When they are, you'd probably want to go with the AIC rather than the BIC. You can extend this to multiple predictors. You could do the same exact thing with, say, yt equals beta 0 plus beta 1, yt minus 1, out to beta p, yt minus p. Let me just use 1x, plus delta 1 xt minus 1 plus, I'm going to call this delta p xt minus p plus ut. For these tests, you usually have the same number of lags, because if we tried every possible combination, if this was Q1 and Q2, we could have p equals 1 and q equals 1, 2, up to p, or whatever, q1, and then we could have p equals 2 and all of those. And if you had many x's, you just get so many models to estimate that it's really hard to keep up with. And so most of the time, if I want to know how many lags to include, I would just set p the same for x and y. And then from then on, you just do it in the same old way. You would take the BIC with k, in this case, k is 1. Would just be the log of sum of square residuals of k and p lags over t, if I make them the same, plus k times, let m, I'm going to use different notation in the book because I don't like the k, because that usually means something else. Let m equal p plus k plus 1 equals the number of coefficients in the model. So there's p, k here, q1. There's q variables here. Here, p equals q. So this would be 2p plus 1. So the number of variables, the number of coefficients is there's p plus 1 betas, and there's p or q1 or q x's. So the total coefficients of this. So the BIC for those m coefficients would be m plus m times the log of t over t. So this is just the number of coefficients in the model. And then the AIC of m would be the same thing, the log sum of squared residuals for m divided by t plus a different penalty. 2 over t is the penalty. M times 2 over t. Before, we didn't have q. Q was 0 because we didn't have any x's. And so in that case, this was p plus 1. So there's really no difference between the two. It's just a slightly different notation. Yeah. All right. Moving right along. Now let's deal with stationarity and figure out what we need to do to overcome this problem of non-stationary models. So again, we'll look at, so let's look at stationarity. There's two common types of non-stationarity. Trends, which we'll deal with first, and breaks, which we'll deal with secondly. So let's talk about the problem with trends. And as I said before, one example of a non-stationary series would be something like, so consider yt is beta 0 plus beta 1t plus ut, where this is normal. It doesn't have to be normal, but it has a mean 0, sigma squared u. Then yt would be distributed normal with mean beta 0 plus beta 1t and a variant sigma squared u. The picture of this is an upward trend, beta naught plus beta 1t, with data scattered all around it due to ut. And what this means is that the homoscedastic is that the distribution of these things looks exactly the same at every point along this line. So there's no heteroscedasticity. These are supposed to be normal distributions of the errors at some point, like here. But the point is that the mean depends upon t, and that means it's non-stationary. So before we could do anything with this, we would have to find a way to make the series stationary. We'll talk about that later. There are two types of trends. The first is what we've been talking about up to this point, deterministic. So in this model, yt is beta 0 plus beta 1t plus ut. This is the underlying trend. And this just gives us randomness about it. And so the trend in this model would be beta naught plus beta 1t. And there's nothing random about it. It's just that's the trend. And so it's deterministic. Another type of trend that we'll have to spend a little more time talking about is stochastic. And this is what is almost always assumed. So this type of trend, you drift upward, but it's very random as you do. And we'll write down a model that generates something like this in a sec. So stochastic, deterministic. So again, I think deterministic is relatively straightforward. Let's spend a little more time on these stochastic trends. So most of the time, what we assume is what's called a random walk model of the trend. It's also called a random walk with drift. And what I'm going to show you in a few minutes is that written properly, this kind of looks like a deterministic trend with a bunch of random stuff going on at the same time. This is like the lag length thing. If you assume a deterministic trend and the true trend is actually stochastic, you'll make these big errors, and we'll talk about what they look like later. If you assume a stochastic trend and the true trend is linear, that's not a big mistake. And so in the reality, it's hard to use the data to distinguish these two things, though we can do it to some extent. We generally, when there's any uncertainty about what type of trend it is, we'll assume a random walk, because if you're wrong, that produces the least costly error. So let's start with a random walk without a trend. And what that looks like is yt equals yt minus 1 plus ut. This is IID generally. All you really need is it's uncorrelated with this, with all the y's. But it's the usual stuff here. So that's a random walk model. The reason is that the change in yt minus 1, is random. And so what you do is you start where you are, and then you take a random step. And then given where you are, you take another random step. And the step could be in any direction. So if you watch someone walking across, according to this model, the gait would just be random. They would just wander all over the place. These are really hard to work with. They have an infinite variance, and you just can't do much with them. This you could work with, because this is just a standard normal. So we'll see later that differencing usually takes care of this. But that's just a basic, what's called a random walk. So what would be the best forecast there? The expected value of yt given yt minus 1 is just yt minus 1. Your best forecast of yt plus 1 would just be yt in this case. The expected value of yt given yt minus 1 is just yt minus 1. The expected value there is 0. So when you have a random walk, your best forecast of tomorrow is where you are today, because where you are tomorrow is totally random. A different model is a random walk with drift. And that, all we do is add a constant. So the ut is still IID, or expected value of ut given past y's is 0, same thing. So now yt plus 1 would be beta 0 plus yt plus ut plus 1. And the expected value then of yt plus 1 given yt would be beta 0 plus yt. So this is the drift. It's where you are yesterday, but you always drift in a particular direction. So you still take a random walk, ut, but this always pulls you in one direction. And these usually look like just a wandering upward path. The reason it goes upward like that, let's play around with this model a little more. Let me show you a different way to represent this model. So I'm going to start at y0. Wherever the world is at y0, that's where we're going to start. Then y1 would be beta 0 plus y0 plus u1, right? Then y2 would be beta 0 plus y1 plus u2, and I'm going to plug that in there. So that's beta 0 plus beta 0 plus y0 plus u2 plus u1. So this would be 2 beta 0 plus y0 plus u2 plus u1. Then y3 would be beta 0 plus y2 plus u3. Plug that in there, play around with it, and you'll get that this is equal to 3 beta 0 plus y0 plus, oops, almost fell down, u1 plus u2, not really, plus u3. Continue iterating. Find the pattern by induction. And you'll find then that yt is t beta 0 plus u1 plus u2 plus ut. Oops, t. Let me call this beta 0t just to make it more like what we saw before. Beta 0t, and that should be t. plus y0. So beta 0 t plus y0 plus this. So this is a deterministic trend. And this is the stochastic, or the random part. So the model tries to drift up over time. Over time, yt tries to drift up. You've got these cumulative errors pushing it around. And so it'll really look like just a random upward walk as you look at it. The fact that this contains a deterministic trend sort of as a special case in some sense, if all the u's were 0, that's why assuming this, if you really have a deterministic trend, is less of an error. Okay. Here's the problem. That random walk with drift is the model almost all macro time series econometricians assume for GDP. But there's a problem. Random walks, both of them that we've looked at, are non-stationary for two reasons. First, the variance increases over time and eventually hits infinity. And the mean increases over time when there's a drift term. So neither the mean nor the variance are constant like we need for stationarity. In fact, we just showed that yt is beta 0t plus y0 plus the sum from 1 to t of the uj. Let's assume y0 equals 0, just to make it easy. Basically, we're setting y at its mean at that point, just to make it easy. Then if the variance here, the variance of yt will be t sigma squared u. So as t goes to infinity, the variance goes to infinity. Basically, this is a deterministic, so it doesn't contribute to the randomness. This is 0. Each one of these has the same variance, sigma squared u. They're independent. And so we get t sigma squared u's. So every time we add another observation, the variance gets a little larger. And that's a problem. And we already saw the expected value goes up over time with these kinds of models, so I won't go back through that. So what we're really talking about is a broader topic called unit roots. So the random walk is a special case of an AR1. So an AR1 would be yt is beta 0 plus beta 1, yt minus 1 plus ut. So it's where beta 1 equals 1. So for a random walk, beta 1 equals 1. If the absolute value of beta 1, and that's non-stationary. If beta 1's less than 1, then the model's stationary. So we really want to know whether beta 1 is 1. If it's bigger than 1, that's a big problem too. or if minus 1 is less than beta 1 is less than 1. That's what this says. In that case, it's stationary. In this case, it won't be. And so why is it called a unit root? I'm not going to go through this more generally, but you can take a model like this, and for an ARP, how do I want to say this? For an ARP, there's something called, I'm not going to ask you about this, the characteristic equation. You need to know about unit roots, though, and what they mean. So for an AR2, it would be 1 minus beta 1x minus beta 2x squared. So this is just like the polynomials you saw in high school or y, wherever you saw them. Y equals this. So it's just a polynomial equation. You can factor this into 1 minus gamma 1x and 1 minus gamma 2x. Those are the zeros. So you can find the zeros of this thing. And so the zeros of this would be, sorry, this is beta. The zeros of this would be 1 over gamma 1 would be where, when x is 1 over gamma 1, this is 0, and 1 over gamma 2. If either of these equals 1, we say there's a unit root. It's probably easier for an AR1. For an AR1, the characteristic equation would be 1 minus beta 1x equals 0. And so it's where x equals 1 over beta 1. If 1 over beta 1 equals 1, then it's a unit root. So that's just the case where you have a unit root when yt equals beta 0 plus beta 1 yt minus 1 plus ut. When this is 1, you have what's called a unit root. So it's about the roots of these characteristic polynomials. But don't worry about that too much. What we're looking for here is the conditions under which the model will be non-stationary. And so the basic test, so if you have yt, it's beta 0, plus beta 1 yt minus 1, plus beta p yt minus p. I'm not going to do the math for this, but if there is a unit root, if it's non-stationary, beta 1 plus beta 2 plus beta p will equal 1. That's not a hard thing to prove. I'll actually show you that for AR1 or 2 later. But this is what we're talking about. This is when one of those roots of the characteristic polynomial would be 1. When this happens, the model is non-stationary. So that's what you need to know. When there's just one lag, it's just when beta 1 equals 1. If there's 2 lags, if beta 1 plus beta 2 equals 1, it's non-stationary. If it's less than 1, then it'll be stationary in absolute value. So that's the test. And that will be a Dickey-Fuller test. We'll come to that in a second. Okay. We are getting there, but we've got a little bit more to do. Chunk of material yet. Let's talk about the problems caused by unit roots, non-stationarity, problems caused by stochastic trends, which is another way of saying unit roots or non-stationarity. because stochastic trends have unit roots and they're non-stationary, which are the same thing. There's three problems. One, if you estimate, let me just do an AR1, yt equals beta 0 plus beta 1, yt minus 1 plus ut, and beta 1 equals 1 is the truth. If you estimate this, beta 1 hat will be biased downward. In fact, the expected value of beta 1 hat is approximately equal to 1 minus, I will never ask you this formula because I didn't know it myself off the top of my head. I knew it was biased. Is that, so for instance, if you have 80 observations, if t equals 80, the expected value of beta 1 hat turns out to be 0.934. So you're way off compared to the true value of beta 1 equals 1. So OLS on non-stationary models just doesn't give you the right answer. Also, and this is still the first problem, it has a long left tail. That is beta 1 hat. The estimator of beta 1 hat has a long tail. So for t equals 80, 5% of the time, on average, expected value, beta 1 hat would be less than 0.824. The authors of your textbook are probably the best time series people anywhere, and they came up with all these estimates long, long ago. So the implication is that if you just naively estimate a model with a stochastic trend with OLS, even more complicated AR models, you're going to get this downward bias and you're going to get really poor forecasts. And if you were searching for the truth, you wouldn't find it. The second problem is you have non-normal distributions of the t statistics. So even if the estimator wasn't biased, and it is, but if it wasn't, your t's would be all messed up. And so you can't use confidence intervals, you can't do any of the usual sorts of things. All your conventional tests are invalid. And the third problem is what we call spurious regressions. Spurious regressions. When two different variables have a trend, they're both drifting upward over time. So you've got some variable yt, and it's drifting up randomly, and some other variable xt over time, and it's also going up. Even if these variables have no causal relationship whatsoever, if you run a regression of this on this, or even this on this, you're going to find a highly significant coefficient. It'll look like one variable causes the other. It'll look like you've discovered something important, but you haven't. I mean, just because, I don't know, what would be a good example? Just because gambling has grown over time in Las Vegas and the number of churches have grown over time, I don't think if I ran a regression of gambling on churches, I would find a significant coefficient because they're both growing. It would look like they're related, but I don't think I'd want to conclude that churches cause gambling. Maybe the reverse causality is true, I don't know. Probably what's really going on there is there's lax regulation allowing both sorts of things to happen. All of the marriage chapels and things and all of the gambling both come from a common cause, which is there's a third variable that's really causing both. And we look at these two things, and they just look like they're related, but they're really not. And so a lot of things grow over time just because the economy is growing. So almost all of the, most macro variables will have this trend just because everything's growing. But it doesn't mean when we regress one variable on the other that there's any sort of causal relationship. And so what we really want to know in those sorts of cases is when one variable deviates from its trend, does that push the other variable away from its trend? That would be a fair test. Okay. So if it causes all these problems, how do you test for it? And what we're going to use is what's called an augmented Dickey-Fuller test. So for an AR1 model, here's what you would do. So you have yt is beta 0 plus beta 1 yt minus 1 plus ut. And I want to know, I want to test, does beta 1 equal 1 versus the alternative? This is a one-sided alternative. Beta 1 is less than 1. So this is, the null is a unit root. Is there enough evidence to reject the unit root in favor of stationarity? So this is the unit root non-stationary case, and this is the stationary case. So how do we test for that? The test is easier using a modified version of this model. So let me show you what we're going to do. What you can do is subtract yt minus 1 from both sides. So yt minus 1 equals beta 0 plus beta 1 minus 1 yt minus 1 plus ut. So delta yt is beta 0 plus delta yt minus 1 plus ut. Now we can just do a standard test. We can just look at the output because the null is that delta equals 0 versus the alternative that it. So delta is beta 1 minus 1. So when beta 1's 1, when there's a unit root, that's the unit root case. When it's less than 1, the alternative is that delta is less than 0. So you just do a one-sided t-test, essentially. So you run this regression, the difference on the lagged level, and you look at this coefficient. Now the problem is that you're going to use the t-statistic from this. So you just run this with OLS. Then you can look at the t-statistic for delta. The problem is it's not distributed t. So we're going to have to use some special tables to look at that. But let me cover the ARP case first, and then we'll talk about how to do the test. But it's basically like a t-test, except you have to look up different critical values. There's a different table for that. Now you can extend this to an ARP model. So for an ARP, delta yt is equal to beta 0 plus delta yt minus 1 plus delta 1, sorry, oh yeah, delta 1, delta yt minus 1 plus gamma. That's why I was screwed up. The different coefficients there. What? Plus gamma p yt minus p plus ut. So you can take an ARP and rewrite it this way. And in this case, this delta will equal 1 minus beta 1 plus beta 2 plus beta p. Remember that I said that with an ARP, if you have a unit root, those things will sum to 1. You can show that. I won't ever ask you to do it. But so it's the same test. So we really want to know, I think I've got the signs wrong. I think it's minus 1 plus. So the null is delta equals 0, and the alternative is delta is less than 0. And so you would run this model. So you'd run the difference of yt on the lag of yt, and then the lag differences. Then just grab the t statistic on this coefficient. But again, so there's an important note. The distribution of the t statistic for delta is non-normal. So we're going to have to use the Dickey-Fuller test tables. You won't have to use the tables. We'll just use the Dickey-Fuller test in Stata. But you need to know that those things are different. So the Dickey-Fuller test can be generalized slightly. So what you generally do, so generally, the model that you use is delta yt is beta 0 plus delta t plus alpha t plus delta yt minus 1 plus gamma 1 delta yt minus 1 all the way out to gamma p delta yt minus p plus ut. So all we've done is add this alpha t term. What that does is it allows us to test, so it allows the null of a unit root yt equals, for an AR, I'll just write the AR1 case, plus yt minus 1 plus ut versus the alternative of yt has a deterministic trend. So this is the test we usually do. You can see from the data that it has a trend. Yt has a trend. Prices have a trend. All these variables have a trend. But what type of a trend is it? Is it stochastic or is it a deterministic trend? And we can answer that by looking at this alpha and this delta coefficient. So the null is alpha equals 0. So this null is alpha equals 0 and delta equals 0. And the alternative is alpha does not equal 0. And yeah, that's basically it. And delta is less than 0. So you don't have a unit root. You have a stochastic trend. You don't have a deterministic trend. You don't have a deterministic trend, but you do have a unit root or a stochastic trend. So that's the test that we're going to be doing. The critical values for the augmented Dickey-Fuller test, the book uses ADF for that. So the critical values for the augmented Dickey-Fuller test are in table 14.4. They're all negative since the test is one-sided, like we've been talking about. So here's an example, straight from the book. So let's look at US GDP, and we want to, the null is a stochastic trend, a random trend, and the alternative is deterministic trend. and stationary. This is non-stationary. So the book runs delta log GDP, not growth, because we want to know if it has a unit root. GDP T equals 0.244. Or wait, this is growth. So we're looking for, is there a unit root here? I'm sorry, this is the level. 0.244 plus 0.0002 times T. 0.109 is the standard error there. 0.0001 plus minus 0.03, the log of GDP at T minus 1, 0.014, plus 0.269 delta log GDP T minus 2, 0.069. So they estimated an AR3 plus 0.178. I'm sorry, an AR2. 0.1, this is T minus 1. Trying to think ahead here and talk at the same time, and it's not working. So let me focus in on GDP of T minus 2, and this is a 0.070. So what we want to know is whether this coefficient is different from 0. And if we use the standard t-test, that's greater than 2, right? The standard error, we double that, we get 0.028. So we're going to get a t greater than 2. We'd reject a unit root with a standard test. But that standard test would be wrong because so the t-stat for this coefficient here, so the t is minus 2.18. But if the 10% critical value from those tables in the back of the book is actually not 1.96 or minus 1.96, but minus 3.12. So we fail to reject a unit root. So we're accepting a stochastic trend instead of a deterministic trend with stationarity. So you can't just look at this t statistic. You run this type of regression, but you can't just look at that t statistic in the normal way. You have to grab the critical value from the right table. So how do you avoid problems caused by unit roots? The most reliable way and the simplest way is to just difference your data. So to solve the unit root problem, use differenced data. That'll work for you. A simple case is yt is beta 0 plus beta 1 yt minus 1 plus ut, where this is 1. That's non-stationary, has a stochastic trend. But if I difference the data, yt minus 1, which is delta yt, that's just beta 0 plus ut. That's just a constant with randomness around it. And that's stationary. The mean doesn't drift. The variance doesn't change. So by differencing it, you get rid of the problem. That goes through generally. If you difference these data, if you have an ARP, you test for unit roots using the augmented Dickey-Fuller test. You find you have one. The solution is to difference the data and then use p-lags. And you've determined the lags from an augmented Dickey-Fuller test. All right, 2 more topics, testing for breaks and then pseudo-regressions. And then we're done with this chapter. So the second type of non-stationarity is breaks in the data. There's 2 types of breaks. You can have a break where you're going along with, say that your model is yt equals beta 0 plus beta 1, yt minus 1 plus ut. Suddenly, both the slope and the intercept, or just one or the other, might change. So you might suddenly have some jump in the data at this point, and maybe even the slope changes. And so you've got some kind of break in not only the intercept, but also in the slope. If you look at US GDP over time, as I was saying earlier, in 2007, you get this drop. It looks like there's some kind of break in the data. And when you have those, the mean of the series is different in one place than the other, and the variance can change and all sorts of things. So it creates a non-stationarity. The other type of break that you can sometimes see are not these abrupt breaks at a point in time, but the model will slowly drift up to some new regime. So it's not like it just suddenly jumps at this point in time to this new point and then goes on the new model, but it takes some time. That second type of break is much harder to deal with econometrically, and we're not going to do that. You would do that in more advanced courses with varying coefficient models. But we're going to look at that first type of a break, where at some point in time, there's some abrupt break, either in the slope or the intercept, or more generally in either beta 0 or beta 1 through beta p. So we're going to look at 2 types. Oh, let's look at the problems. Yeah, you just get non-stationarity. The book goes through the problems caused by breaks. It's that the future is different than the past, so you're not going to forecast very well. So testing for breaks. How do you do that? There's 2 different techniques, and it depends upon whether the date is known or unknown. So when the breakpoint is known, we can use a standard dummy variable test that we've looked at in the past. Now, there's a caution here that even the book cautions, and I agree, even when you think you know the breakpoint, like I think I know that monetary policy changed in 1982, you probably don't for various reasons. So in general, you probably want to, the second type of test will be when the breakpoint is unknown. That's probably the test you want to do most of the time, unless you're absolutely certain you know the breakpoint is this particular day on this date with certainty. To illustrate, let's use an autoregressive distributed lag 1, 1. That is yt is beta 0 plus beta 1, yt minus 1 plus delta 1, xt minus 1 plus ut. Now let t0 be the breakpoint. So you've got one model up to t0, and after that, some other model altogether. It probably wouldn't change the sign of the slope, but it's just some other model from that point on. Drew that terribly. You get the idea. So we know t0 is the breakpoint. Then you just define dt, a dummy variable indexed by t0, equals 1 if t is greater than t0, and 0 if t is less than or equal to t0. So we just define a dummy variable, and then you would run the model yt equals beta 0 plus beta 1 yt minus 1 plus delta 1 xt minus 1 plus gamma 0 dt t0 plus gamma 1 dt of t0 times yt minus 1 plus gamma 2 dt of t0 x t minus 1 plus ut. So this gamma 0 allows for a break in the constant. This allows for a break in beta 1, and this allows for a break in beta 2. So before t0, all of these things are 0. So the model is just this model. So before t0, it's yt equals beta 0 plus beta 1 yt minus 1 plus delta 1 xt minus 1 plus ut. Then after t0, where did I define this? At or after t0. The intercept, this will be 1 here after t0. So the intercept would be beta 0 plus gamma 0. The coefficient on yt minus 1 would be beta 1 plus gamma 1 on yt minus 1. And the coefficient on xt minus 1 would be beta 2 plus gamma 2. So the test is just our gamma 0, gamma 1, and gamma 2, 0. So you would just do an F test of gamma 0 equals gamma 1 equals gamma 2 equals 0 versus at least 1, not 0. And these are called Chow tests. And they're for known breakpoints. You can extend, if you had a yt minus 2, and you'd have a gamma 3, dt yt minus 2, and so on. So you can keep adding these dummy variables to allow different breaks. If you only thought the break was in a constant and you had a good reason to, you could leave out the other terms and so on. But this is a general way that you would use the F-test approach. Mostly you don't know where the breakpoint is. So what do you do? How do you testing for a break at an unknown date? So you have this data set that goes from 1 to t. What we're going to do is set these two limits, tau 0 and tau 1. This is usually at the 15% of the data point, and typically this is 85%. And then we're going to do a Chow test for every possible breakpoint between tau 0 and tau 1. We can't get these too close to the endpoints, because remember, we're defining a dummy variable. If we get too close to this, if we start at 1, we wouldn't even have a dummy variable. At 2, that dummy variable would only be defined for one period as 0 and every other period to be 1. That's just not enough to get a good test. And so what we do instead is to move the endpoints away from 1 and t, and then we run a chow test at every possible breakpoint. So you do a chow test, then you use the largest f. Remember, the chow is an f test that gamma 0 equals gamma 1 equals gamma 2 for the ADL11 equals 0. So you use the largest f to test for a breakpoint. And this is called in the book the QLR statistic. So the distribution of that statistic, so the distribution depends upon where you set those endpoints and the number of breakpoints. There may be more than one breakpoint in the data. Usually we're going to assume just one for us. But the distribution of that statistic depends upon those things. If you assume that this is 0.15 of the data and this is 0.85, they're at those percentiles, then the critical values for the test are on page 565. It's table 14.5. Basically, the critical value is larger than usual for an F statistic because you've looked at so many Fs, you've increased the chance of rejection just randomly. So you want to allow for that by making your critical value larger than it was before. All right. So the properties of the QLR test. Oh, before we get to the properties, on the empirical assignment for this chapter, we're not going to do exactly this test. We're going to do something very close to this test. It actually wasn't in Stata that I could find. If it is there, I just didn't see it. It's basically the same test, and I'll explain that on the video. Again, it's just a matter of pushing the right buttons. So the properties. The breakpoints. The breakpoint is estimated consistently. So it's a consistent estimate of the breakpoint. That's nice. It rejects the null with a higher probability if there are multiple breaks. And there may be. You only test for one, but that doesn't mean there isn't more. So rejection does not mean that you just have one break. It means you have at least one. But if that test is rejected, then you really want to start thinking hard about how to handle the breaks. And the best way is with those dummy variables like we used before. So you just run the model with the dummy variables in it. So avoiding the breaks is not too hard once you've identified them. Okay, last thing, pseudo out of sample. Forecasting. Not Prudo. Pseudo. All right. Ooh. So the ultimate test of a forecasting model is, of course, its ability to predict out of sample, its ability to forecast. What we can do is we have these data that go from 1 to t. So maybe this is, I don't know, 2007 Q4. And this is 1982 Q1, something like that. So that's our data set. What we've been talking about is forecasting out of sample, this t plus 1, the 2008 Q1 variable so far. What you can do here is artificially pick a breakpoint. So let's pick a breakpoint here at 2000 Q1. So this is t minus t0 of some value. You would estimate the model from 1982 Q1, from t equals 1 to t minus t0, 2000 Q1. I'm sorry, 1999 Q4. This is the first period we want to forecast. So you'd estimate the model to 1999 Q4. Then you'd forecast 2000 Q1. And then you can calculate the forecast error and the root mean square forecasting error for that. Okay. You could then estimate the model. You could now do two things. You could also just keep your data ending at 1999 Q4 and then estimate all the way out to t and evaluate how well it forecasts way out. But what we're interested in finding out is not that, but how well does it forecast one period ahead. So this is one example. And it's just like if I was a forecaster at 1999 Q4, it's a pseudo out of sample forecast because this is exactly what I'd have to do. And then I could wait till 2000 Q1 and then evaluate my forecast. But this way, since I already have the data, I can pretend like I'm this person in 1994, but I don't have to wait to see how well I did. Then I would estimate the model from 1982 Q1 through 2000 Q1, and then forecast 2000 Q2, calculate the root mean square forecasting error. Now I've got two different ones. I could average the two of them to see sort of what the average means, average forecasting error is. Then we just continue this. So now we'd estimate the model the third time. We'd estimate from 82 Q1 through, what did we just forecast? 2000 Q2, and then forecast 2000 Q3, and then calc the forecast error and so on. Continue until you estimate from 82 Q1 through, where's my data end? I think I said 2007 Q4. Let's pretend like that's what I said. Through 2007 Q3, and then you'd forecast 2007 Q4, and that's as far as you can go, because the next one we wouldn't have, and find the forecast error and so on. So you just keep doing these one step, you keep adding one to your sample and forecasting one ahead. So you'd have a whole bunch of these forecasts. You'd have, what, 8 years by 4 quarters. You'd have 32 forecasts. You could then look at the average root mean forecasting error for those 32 forecasts, and that would give you sort of, here's how well the model forecasts on average. And so you'll have a problem like that on the homework, or on the empirical assignment. Okay, well, we are at the end of chapter 14, so one more to go. So I'll see you again when we do chapter 15.